A heavy winter storm consists of macroscopic aggregates, clusters of ice that collide and clump together during their atmospheric descent. When isolated, these clumps reveal their constituent parts, snow crystals. Each is a single crystal characterized by a perfectly symmetrical lattice grown directly from vapor. This creates a physical paradox. The atmosphere is a high-entropy environment defined by turbulence and unpredictable wind, yet it consistently produces structures with six-fold geometric precision. These structures form through deposition, a phase transition where supersaturated water vapor in the clouds condenses directly into solid ice, bypassing the liquid phase. While meteorology explains the scale of the storm, it cannot account for the geometric perfection of the individual crystal. To understand that symmetry, we must look at the solid-state molecular physics of the ice itself. Human fascination with this six-fold geometry dates back over 2 millennia, appearing in Chinese records as early as 135 BC. In 1611, Johannes Kepler attempted to resolve the origin of this symmetry, hypothesizing that it resulted from the densest possible packing of microscopic spheres. For centuries, empirical study was blocked by the extreme fragility of the ice. In low humidity, a micro-thin crystal will rapidly sublimate back into vapor. This process destroys the geometric facets before they can be accurately observed or recorded. Moving the study of snow from philosophical theory to empirical physics required a method to capture these structures before they vanished. Almost all snow on Earth consists of a crystalline phase known as ice IH, the most stable form of ice under terrestrial pressures. At the molecular level, one oxygen bonds to 2 hydrogens, replicating to form a lattice of puckered hexagonal rings. This internal order, space group 194, mandates the crystal's six-fold symmetry. This atomic arrangement scales up into a hexagonal prism, defined by flat basal and prism facets. Molecules hook up locally into these flat planes through a stabilizing force called faceting, which minimizes the total surface energy of the crystal. The hexagonal shape we see in a snow crystal is a direct, macroscopic manifestation of this sub-nanometer atomic architecture. Confirming that these crystals grow into diverse shapes required shifting to sub-zero empirical data collection. In the 19th century, Bentley defeated sublimation by mating a compound microscope to a bellows camera, capturing the crystals on glass plates. Bentley's archive of 5,000 photographic plates provided the first proof of massive structural variation, showing the lattice growing into needles, hexagonal columns, and flat plates. By the mid-20th century, physicist Ukichiro Nakaya began to systematically categorize these variations in a controlled environment. Nakaya grew the first artificial snow crystals in his lab, isolating and testing how different environmental variables changed the growth of the lattice. This work transitioned the study of snow from an artistic curiosity into a quantifiable dataset of condensed matter physics. These experiments led to the Nakaya morphology diagram, which maps how specific environmental conditions command the final shape of the crystal. The diagram shows that the primary driver of crystal shape is temperature. This is governed by attachment kinetics, the thermodynamic preference of water molecules to bond to basal or prism planes. Condensing on prism planes creates flat plates at -2 degrees, but at -5 degrees, molecules attach to basal facets, creating long columns. This system is incredibly sensitive. A temperature drop of just 3 degrees can shift the dominant growth rate by a factor of 1,000, fundamentally altering the crystal's architecture. The basic blueprint of the crystal is strictly commanded by its local thermodynamic state. If faceting were the only force involved, every snow crystal would be a solid, simple hexagonal block. But high humidity gradients in the atmosphere provide a competing, destabilizing force. In supersaturated air, the Mullen-Sakirka instability drives spontaneous complexity by breaking the symmetry of flat facets. Because the hexagon's corners stick out slightly further, they reach into zones of higher humidity. This creates a runaway feedback loop, accelerating growth and sprouting a dendrite arm. The intricate beauty of a snowflake is the result of a physical tug-of-war between the molecular order of faceting and the environmental instability of branching. A falling snow crystal serves as a physical flight data recorder, preserving a history of its atmospheric descent in ice. During its fall, the crystal moves through alternating strata of temperature and humidity. Each time it crosses into a new stratum, its growth pattern changes. It might shift from branching dendrites to capping those branches with flat plates, then back again. Atmospheric turbulence ensures that no two crystals follow the exact same path. Because their journeys are different, their final morphological records are infinitely unique. However, because the crystal is only millimeters wide, all 6 arms experience the same microclimate at the same time. They grow in perfect synchrony. Macroscopic symmetry is not pre-programmed. It is the result of synchrony acting across the crystal's diameter. At the micro level, we can easily see that even a massive winter storm is a site of highly organized physics. Every falling crystal is defined by the conflict between local molecular alignment and diffusion-limited instability. These crystals serve as natural laboratories for understanding pattern formation. The physics governing these branches provides insights into metallurgy and nanoscale self-assembly. What began as an aesthetic wonder is now a foundational case study in non-equilibrium thermodynamics. The snow crystal is proof that nature can spontaneously organize